Hi, this is Mrs. Barber. This is AP Physics Mechanics C. Today's topic is simple harmonic motion part 2. The objectives are note kinematic characteristics of spring mass system in simple harmonic motion in relation to time. Understand simple harmonic motion is projection of uniform circular motion onto a diameter. Be able to derive a differential equation from Newton's second law for spring mass system in simple harmonic motion. Be able to relate period frequency and angular frequency to mass, spring constant, and amplitude. Be able to calculate position, velocity, and acceleration with given time or given initial condition, mass, and spring constant. First, let's figure out speed and acceleration of simple harmonic motion. So for last part 1, we already figured out x. For simple harmonic motion, the displacement equals a cosine omega t plus phi. This is a general sinusoidal function. So sometimes it can be sine. It depends on your phase angle, phi. From here, we can figure out velocity. Velocity is dx over dt. It's a simply derivative. Derivative of cosine is negative sine. Remember, here's omega t. You have to use the chain rule to get omega. So Vx equals a negative omega a sine omega t. This tells you the maximum value of Vx is omega a. Where does this happen? This happens at equilibrium position. You can imagine it right in the middle. That's when the object moves fastest. It can go in either to the right, positive, or to the left, negative. When is v equals to 0? V equals to 0 when this part equals to 0. When does that happen? That happens at the end. The maximum displacement positions can be most negative or most positive. Next one, let's take a look at acceleration. Acceleration is derivative of Vx over dt, dvx over dt. So again, negative omega a, derivative of sine is cosine. Again, using chain rule, we can get another omega. So ax is negative omega squared a cosine omega t plus phi. See this? Omega a cosine omega t plus phi, that is your x. So ax equals a negative omega squared x. This is the hallmark of simple harmonic motion. So whenever you know, if you see a function like this, you know it's simple harmonic. Or if you are given motion is simple harmonic motion, you know it satisfies the condition like this. Let's see what are special points. Ax equals to 0 when x equals to 0. So at equilibrium position, there is no acceleration because there's no force. Ax is the most positive at x is when x is most negative, and ax is most negative when x is most positive. This is at maximum and minimum displacement position. And here is an animation kind of tell you when is, see right in the middle, ax equals to 0, x equals to 0, but Vx is maximum. At the end, both x and ax are maximum, but Vx equals to 0. Remember those points, special points. Kinematic equations are sinusoidal functions of time. This is again because the motion is the projection of uniform circular motion onto its diameter. That's why we have to find adjacent. That's why it's cosine. Okay, let's take a look at the graphs. Here is special case when phi equals to 0. When phi equals to 0, x is just a cosine function. When phi equals to 0, Vx is a negative sine function, so that's a negative sine function. When phi equals to 0, Ax is a negative cosine function, so that's a negative cosine function. If you compare this to Vx, is Vxt graph is shifted by pi over 2 or quarter cycle from the xt graph. Axt graph is really shifted by pi over 2 or quarter cycle from Vxt graph, and by pi graph from xt graph. So basically it's the same graph, you just shift a quarter become Vx, you shift a half cycle becomes A. Okay. apply Newton's law for simple harmonic motion. So here is a diagram for simple harmonic motion. Here are the forces acting on the object. Normal force and gravity cancels out. So this Fx is the net force. When Fx and x are always in the opposite direction. When x is positive, Fx is negative. At the equilibrium position, there is no Fx because the spring is neither stretched or compressed. Normal force and mg cancels out. Net force equals to 0. When the spring is compressed, x is negative and Fx is positive. Again, Fx is just the net force. From Newton's second law, we know F net equals to ma. So what is F net? F net in this case equals negative kx. So we have max equals negative kx. From here, we can solve for ax is negative k over m. Sometimes we can write this as differential equation to solve it mathematically, and this will give us the sinusoidal functions. So this is a function for sinusoidal function. Okay. So that's C. We also know ax equals negative omega squared x. When we derive ax equals to dx over dt squared, we know what x equals to, right? Now compare these two functions. You know omega squared has to be equals to k over m. So we know omega equals k over m. What's omega? Omega is angular frequency or angular speed. Angular frequency and angular speed are the same thing. Basically is how many rounds does it go? How many cycles, total cycles does it go in 1 second? T, F, and omega are related to mass and spring constant, but not to A. Let's take a look at the equation. Here is omega. Remember, omega is defined how many radians per second, so it's really 2 pi f. So it's f equals 1 over t, so omega equals to 2 pi over t. Hence, we got f. How f relate to k and m is the same as omega, but t is inverse because f and t are inverse related. So t equals to 2 pi m over k. What does this equation tell us? Period and the frequency of a simple harmonic motion are completely determined by the mass m and the force constant k. They do not depend on amplitude a. Larger amplitude means the body reaches large value of x and is subject to larger restoring force. This increases the average speed of the body over a complete cycle, and this compensates of having to travel larger distance. So the same total time is involved. Period, it does not depend on the amplitude. How mass, a spring constant A affect the period? We know the period does not depend on amplitude. This is what happens to the period. It's only the maximum value of x increases. The period at the time does not change. What happens when you increase the mass? See, the blue is the first. Purple, you increase the mass. The third one, the gold, you increase mass even more. So it seems like you're stretching it. Increasing mass, T increases. What happens? You increase K, have the same A and M. When you increase K using this equation, T decreases. So here is the blue is the original one. The gold is the last one. You kind of compress the wave. So T actually decreases. Let's take a look at this example. A spring is mounted horizontally, which is left with its left end held stationary. By attaching a spring balance to the free end and pulling toward the right, we determine the stretching force is proportional to displacement. That is a force of 6 newtons equals the displacement 0.03 meters. So this basically tells you F equals negative kx, obeys Hooke's law, so the motion has to be simple harmonic motion. We remove the spring balance and attach a 0.5 kilogram glider to the end, pull it 0.2 meters along a frictionless air track, release it, and watch it oscillate. First, we have to find the spring constant. For that, we can use Hooke's law. We know the force, we know the displacement, we can find K. Using that equation, K is Newton per meter. This is equivalent to kilograms per second. Next one, we have to find angular frequency, and the period. We know angular frequency, how they relate to mass and K. We know the mass already, 0.5. We know K is 200. Simply substitute your numbers in. So from this equation, you should realize that you really didn't need amplitude to calculate angular frequency, or period, because they are independent of amplitude. So let's see, what's the takeaway? In this lesson, we've learned the cause of all oscillations. That's because of restoring force. Because of that, restoring, so force and displacement are in the opposite direction. Consequently, acceleration and the displacement are also in the opposite direction. The hallmark of simple harmonic motion is this: ax equals negative omega squared x. Kinematic characteristic of spring mass system in simple harmonic motion in relation to time. This one says when x is maximum, ax is minimum, most negative, and v equals to 0. When x equals to 0, in those cases, v is either maximum negative or maximum positive, and a are 0. The terms and the equations that describe simple harmonic motion, these are the terms and equations are sinusoidal waves. Okay, so terms is amplitude, period, frequency, or angular frequency. They are sinusoidal waves functions because simple harmonic motion is the projection of uniform circular motion onto the diameter. Period, frequency, and angular frequency, they relate to each other and they relate to mass and spring, and this is how they relate. When mass decrease, omega increase, and when K increase, omega increase, and so forth. Remember how period change, increase the mass, period increase, decrease mass, period decrease. When you increase K, T decrease, and so forth. Remember the relationship. Be able to derive differential equation from Newton's second law. Newton's second law start with F equals to ma. And for simple harmonic motion, F equals to kx. So max equals negative kx. So, and the differential equation is just this. We can solve x from this differential equation. This will give us sinusoidal functions as well. Be able to calculate position, velocity, acceleration with given time. This we have to use sinusoidal functions, plug in the time, or if we know the initial condition, mass, and spring, we can also find other position at the time, velocity, and acceleration. So let's take a look at another example. Spring is mounted horizontally. We know the K, we know the M, we know the initial condition, initial displacement, and initial velocity. First, we have to find the period. We have to find phase angle and amplitude. So period is easy. Period equals to 2 pi m over K. We know M, we know K. So we can find the period. We can find omega, angular frequency. How do we find the phase angle and amplitude? So from the displacement function, when t equals to 0, x naught equals a cosine phi. We know x naught, but we have two unknowns. But we also know velocity function. So initial velocity, now we also know. So two equations have two variables, a and phi. So basically you just manipulate this and trying to find one. So there are different ways to do it. I chose to divide this. When I divide this, I can get rid of a. So the only thing I don't know is phi. Then I can find phi using inverse 10. Substitute all the numbers. Next, once I know the phi, I can find a by just substituting into either equation. If I choose the first one, I get a equals to 0.25, 0.25 meters. Okay, part 2, we need to write equations for displacement, velocity, and acceleration. Here are the conditions we know. So x equals to a cosine omega t, simply substitute the given quantities. And here is v, and here is a. So what does this tell us? The displacement varies from the positive 0.025 to the negative 0.025. Vx varies from negative 0.5 to positive 0.5, and here's ax varies from negative 10 to positive 10. You can check the result by setting t equals to 0. And that's it for today. Thanks for watching.